In this video, we'll explore how to functionalize alkanes through free radical halogenation. We'll start by introducing homolytic bond cleavage, bond dissociation energy, and the properties of radicals, followed by the factors that influence their stability. Next, we'll dive into photochemical and heat-induced chlorination and bromination, discussing the free radical chain mechanism, including initiation, propagation, and termination. We'll then explore the thermodynamics and kinetics of these reactions, rationalizing the differences in selectivity between chlorination and bromination using the Bell-Evans-Polanyi principle and the Hammond postulate. Finally, we'll cover allylic and benzilic resonance, allylic bromination using NBS, and conclude with the stereochemical implications of radical reactions. Up until now, we've discussed alkanes as saturated hydrocarbons that are generally unreactive and primarily serve as the backbone for most organic molecules. It turns out we can functionalize alkanes through halogenation, where a halogen, typically chlorine or bromine, replaces a hydrogen atom on one of the carbons in the alkane, forming a haloalkane, also known as an alkyl halide. Alkane halogenation does not occur via the same mechanism as acid-base reactions. You may recall that alkane CH bonds are very strong, making them difficult to break. For example, when water and methane are treated with a strong base like sodium amide, NaNH2, one of the OH bonds in water is easily broken to form hydroxide, OH-, whereas none of the CH bonds in methane break to form a methyl anion, CH3-. Based on the pKa's of species in the two reactions, we can see that it is favorable to break an OH bond to form a NH bond, while it would be unfavorable to break a CH bond in favor of forming a NH bond. Based on this observation, it would be even less likely that halogenation occurs via a similar mechanism, as a chloride or bromide anion are significantly weaker bases than sodium amide, making the reaction many orders of magnitude more unfavorable. What's even more peculiar is that the OH bond in water has a bond dissociation energy of about 119 kcals per mole, while the CH bond in methane has a bond dissociation energy of around 104 kcals per mole. This seems contradictory. pKa values tell us that the OH bond in water is more acidic than the CH bond in methane, implying that the OH bond is weaker. However, bond dissociation energies suggest the opposite, with the OH bond being stronger than the CH bond. We can understand this phenomenon by first defining bond dissociation energy. Bond dissociation energy is measured through calorimetry of radical reactions, and therefore represents the energy needed to break apart a bond into two radicals. While acid-base reactions proceed via heterolytic bond cleavage, where both electrons in a bond are transferred to one atom, homolytic bond cleavage occurs when the two electrons in a bond are evenly split between the two atoms. This leaves each atom with an unpaired electron, resulting in the formation of two radicals. Unlike heterolytic bond cleavage that uses double barbed arrow pushing formalism to depict the movement of electron pairs, homolytic bond cleavage uses single barbed arrow pushing to show the movement of single electrons. Therefore, we can conclude that bond dissociation energies reflect radical stability, not acidity. Let's briefly discuss some key properties of radicals before exploring the factors that affect their stability. Radicals contain a lone, unpaired electron, which resides in a half-filled p orbital that is perpendicular to the plane of the bonding electrons. This often leads to a trigonal, planar-like geometry around the radical center, influencing their reactivity and the products they form. Additionally, because radicals have an unpaired electron, they are highly reactive, making them prone to fast reactions with other molecules in an effort to achieve a more stable paired electron configuration. Stabilizing an unpaired electron is different from stabilizing a non-bonding pair of electrons, and different factors influence their stability. Since radicals are electron-deficient species, any factor that can either donate electron density to the half-filled orbital or delocalize the unpaired electron over a larger volume will help stabilize the radical. Let's go over just a few factors that affect radical stability. Number 1. Radical stability increases as the carbon from which the hydrogen atom is abstracted becomes more substituted, progressing from methyl to primary, secondary, and tertiary. This is because more substituted carbons have nearby alkyl groups that can donate electron density through inductive effects, helping to stabilize the electron deficient radical. Notice that the bond dissociation energies decrease as the carbon in the CH bond becomes more substituted, with methyl having the highest bond dissociation energy and tertiary having the lowest. Number 2. Going down the periodic table, free radical stability increases with the size of the atom. For example, when comparing halogen radicals, the larger iodine atom stabilizes the radical better than the smaller fluorine atom. This is because iodine's larger orbital spreads out the unpaired electron over a greater volume, and since the electron is farther from the nucleus, it experiences less effective nuclear charge than it would in a smaller atom like fluorine. We observe this trend in the relative stabilities of halogen radicals, with iodine being the largest and most stable, followed by bromine, then chlorine, and finally fluorine as the least stable. Number 3, free radical stability decreases when the half-filled orbital is held closer to the nucleus. The farther the orbital is from the nucleus, the more effectively the atom can stabilize the radical, as the unpaired electron experiences less attraction from the nucleus. As a result, alkyl radicals are more stable than alkynyl or aryl radicals, which are, in turn, more stable than alkynyl radicals. Another important factor that affects the stability of radicals is resonance. Radicals that can delocalize their unpaired electron through resonance are more stable. We will revisit this concept in more detail later in the video. Now that we've familiarized ourselves with radicals and the factors that influence their stability, let's move on to discussing how they behave in the context of free radical halogenation. Free radical halogenation proceeds through a free radical chain mechanism. Let's take some time to walk through each of the steps in this chain mechanism, starting with the first step, initiation. In the initiation step, the bond between two halogen atoms in a diatomic halogen molecule, X2, where X is a halogen such as chlorine, Cl, or bromine, Br, is homolytically cleaved by energy from light, photochemical initiation, or heat. This process generates two highly reactive halogen radicals. Bond breaking requires an input of energy, which typically comes from heat or light. During the initiation step, this energy breaks the bond between two atoms, increasing the number of free radicals, in this case from 0 to 2 radicals. Following initiation, the newly generated halogen radicals react with a CH bond in an alkane, breaking the bond and forming a carbon radical. This reaction also results in the formation of an HX bond. This first propagation step is referred to as the hydrogen atom abstraction step, which is the rate-determining step of the chain mechanism. We will revisit the significance of this step later in the video. After the carbon radical is generated, it reacts with a molecule of diatomic halogen, X2, to form the haloalkane product and regenerate a halogen radical. This newly formed halogen radical can then abstract a hydrogen atom from another alkane molecule, continuing the chain reaction. Because X2 is required in the second propagation step, it's important that during the initiation step there is only a small concentration of halogen radicals compared to diatomic halogen molecules. This way, there are enough diatomic halogen molecules present for the second propagation step to occur. In the propagation phase of the reaction, the number of radicals remains constant. During the hydrogen atom abstraction step, a CH bond is broken by reaction with a halogen radical, generating a carbon radical and forming HX. Similarly, in the second propagation step, the carbon radical reacts with a diatomic halogen molecule X2, breaking the XX bond and forming a CX bond while generating a new halogen radical. This cycle of radical generation and propagation continues until the reaction reaches the termination step, where any two radicals combine, effectively stopping the reaction. In termination, there is always a net decrease in free radicals. Two radicals come together to form a stable product, resulting in 0 radicals in the final product. Just now, we discussed the free radical chain mechanism of radical halogenation using a general R group and a general halogen, X. Now, let's move on to the reactivity of chlorine and bromine with differently substituted alkane substrates. Here are a couple experimental observations. Observation 1. In the halogenation of methane, methane reacts with a chlorine molecule under photochemical or heat conditions to produce chloromethane and HCl. However, when the same reaction is performed with bromine instead of chlorine, no reaction occurs. Observation 2. In the halogenation of isobutane, isobutane reacts with a chlorine molecule under photochemical or heat conditions to produce two monochlorination products, 2-chloro-2-methylpropane and 1-chloro-2-methylpropane in a 5.61 ratio. Meanwhile, bromination under the same conditions yields 2-bromo-2-methylpropane and 1-bromo-2-methylpropane in a 182-to-1 ratio. Observation 3. In the halogenation of methylbenzene, methylbenzene reacts with a chlorine molecule under photochemical or heat conditions to primarily produce chloromethylbenzene. No orthometa or parachloroproducts are recovered. These three observations make a few key suggestions. In observation 1, radical chlorination occurs even with the less favorable methyl substrate, while bromination does not. The CH bond dissociation energy of methane is relatively higher compared to more substituted alkyl substrates, primarily because methane lacks inductive electron donating effects from surrounding carbon atoms. This means that breaking the CH bond in methane is more energy intensive than in more substituted alkanes. However, chlorination still proceeds, indicating that the overall reaction is exothermic and the hydrogen abstraction step is slightly exothermic. This allows chlorine to react even with less favorable substrates like methane. In contrast, bromination does not occur, suggesting that the hydrogen abstraction step in bromination is endothermic, requiring more energy to proceed. As a result, bromine is less reactive and more selective, favoring reactions that form more stable radicals. Observation 2 makes a similar suggestion. Chlorination produces both products in notable amounts, with only moderate selectivity for the more substituted carbon. In contrast, bromination is highly selective, favoring abstraction of the hydrogen from the more substituted carbon, producing the major product in significantly larger amounts. This suggests that bromination is much more selective than chlorination, likely due to the endothermic nature of the hydrogen abstraction step in bromination, which favors the formation of the more stable radical. Finally, observation 3 suggests that vinyl hydrogens are much more difficult to abstract than benzylic hydrogens. This is because the resulting benzyl radical is highly stabilized by resonance with the aromatic ring, whereas the vinyl radical, formed from a double bond, lacks such stabilization and is therefore much less favorable to form. These observations are consistent with the factors affecting radical stability that we discussed earlier. More substituted radicals are favored over less substituted ones due to greater stabilization through inductive effects, and vinylic radicals are significantly more unstable than alkyl radicals. Now we can put all the pieces together to discuss the reasoning behind the selectivity of bromination versus chlorination. Recall that earlier in the video, we learned that the hydrogen atom abstraction step is the rate-determining step of the free radical chain reaction. To understand the difference in selectivity, let's consider the bond dissociation energies involved in the free radical chlorination and bromination of propane, an alkane with both primary and secondary carbons. The energy required to break the CH bond varies depending on whether the hydrogen is attached to a primary or secondary carbon, and this difference plays a key role in the selectivity of the reaction. The following reaction coordinate diagrams represent the hydrogen atom abstraction step for the formation of both possible radical products in chlorination and bromination. While the relative energy differences in the radical products are the same in both reactions, these diagrams will help us visualize how the differences in transition state energies influence the overall selectivity of these reactions. In the reaction coordinate diagram of the first propagation step in chlorination, we see that both the primary and the secondary radical products are lower in energy than the starting material, indicating that this is an exothermic reaction. Looking further into the diagram for chlorination, we see that this reaction proceeds via an early transition state, meaning that the transition state resembles the reactants more closely, both structurally and energetically. This is consistent with the Hammond postulate, which suggests that in exothermic reactions, the transition state more closely resembles the reactants. As a result, the activation energy difference, Delta delta H double dagger between forming the primary and secondary radicals is relatively small, approximately 1 kcal per mole. This small difference explains why chlorination is less selective. The energy barriers for the formation of both primary and secondary radicals are not significantly different, allowing both to form relatively easily, although the secondary radical is still slightly favored due to its greater stability. Additionally, according to the Bell-Evans-Polanyi principle, for similar reactions, the reaction with the lower delta H should have a lower activation energy and thus the greater rate constant. Since chlorination is an exothermic reaction, the overall energy barrier is lower, allowing the reaction to proceed rapidly but with less selectivity. Because of the lower energy difference between the pathways, chlorination doesn't strongly differentiate between primary and secondary radical formation. Therefore, while chlorination is fast, it sacrifices selectivity in favor of speed. In this reaction coordinate diagram for bromination, we can immediately see some key differences from chlorination, particularly in terms of selectivity and transition state structure. While the relative energy difference between the primary and secondary radicals remains the same as in chlorination, about 3 kcals per mole, bromination is more selective for the formation of the secondary radical due to a larger difference in activation energy, delta delta H double dagger. According to the Hammond postulate, bromination proceeds via a late transition state, which more closely resembles the radical products both structurally and energetically. This is indicative of an endothermic reaction like bromination. The late transition state means that the activation energy difference between the formation of the primary and secondary radicals is larger, approximately 2.5 kcal per mole, compared to 1 kcal per mole in chlorination. This larger energy difference is key to bromination's high selectivity for the more stable secondary radical. In bromination, the secondary radical is strongly favored over the primary radical due to its greater stability from inductive effects. Because the transition state is closer in energy to the radical products, the difference in radical stability plays a more significant role in determining the outcome of the reaction. As a result, bromination overwhelmingly favors abstraction of hydrogen from the secondary carbon. Additionally, according to the Bell-Evans-Polanyi principle for similar reactions, the reaction with the higher delta H should have a higher activation energy and thus the lower rate constant. The endothermic nature of bromination, combined with its late transition state, means that the reaction pathway leading to the more stable radical, the secondary radical, is strongly favored over the less stable primary radical. For every order of magnitude change in the product ratio, the corresponding change in activation energy of the transition state is approximately 1.36 kcals per mole. For chlorination, the change in activation energy between the transition states is close to 1 kcal per mole, which corresponds to a product ratio close to 1 to 10, favoring the secondary radical product over the primary. In contrast, for bromination, the change in activation energy between the transition states is close to 2.5 kcals per mole, which corresponds to a product ratio closer to 1 to 182, primary to secondary, or about 2 orders of magnitude greater selectivity for the secondary radical product. Finally, let's take a look at one more reaction, allylic bromination with N-bromosuccinimide, NBS. Before getting into the reaction, let's do a quick review of some important terminology. The vinylic position refers to the position of a hydrogen or substituent that is directly attached to an alkene's sp2 hybridized carbon atom. For example, in propylene, here are the vinylic hydrogens in red. The allylic position refers to the position of a hydrogen or substituent that is attached to a carbon atom adjacent to an alkene's sp2 hybridized carbon atom. Here are the allylic hydrogens in propylene in blue. Allylic CH bonds have significantly lower bond dissociation energies than even tertiary CH bonds, making them easier to break and more reactive in radical reactions. This is because allylic radicals are stabilized by resonance, which allows the unpaired electron to be delocalized over a larger area, stabilizing the radical. The unpaired electron is particularly stabilized when adjacent to a pi bond. The sp2 hybridization of the carbon atom bearing the radical enables the half-filled p orbital to overlap with the p orbitals of the adjacent double bond, resulting in the delocalization of the unpaired electron across multiple carbon atoms. This delocalization, best visualized through resonance structures, spreads the radical character, lowering the overall energy and increasing the radical's stability. Resonance structures for radicals are typically drawn using single barbed arrow formalism to indicate the movement of individual electrons, as shown below. Benzilic CH bonds are similar to allylic CH bonds in that they also have relatively low bond dissociation energies, making them easier to break in radical reactions. This is because benzilic radicals are stabilized through resonance with the adjacent aromatic ring, allowing the unpaired electron to be delocalized over the pi system of the ring. The sp2 hybridization of the benzilic carbon atom allows the half-filled p orbital to overlap with the p orbitals of the aromatic ring, resulting in delocalization of the unpaired electron across multiple carbon atoms. Just like in allylic radicals, this delocalization, represented through resonance structures, spreads the radical character, reducing the overall energy and increasing the stability of the radical. Resonance structures for benzilic radicals are also drawn using single-barbed arrow formalism to indicate the movement of single electrons. Now, let's apply this understanding of radical stability to allylic bromination using N-bromosuccinimide, NBS. NBS is a particularly useful reagent because it provides a controlled, low concentration of bromine radicals. The reaction begins when a trace amount of HBr reacts with NBS to produce Br2 and succinimide, as shown below. The presence of a constantly low concentration of Br2 allows selective bromination at the allylic position, ensuring that only the allylic bromination product is recovered rather than overbrominated products such as dibromides. Consider the following reaction. When propylene is treated with N-bromosuccinimide, NBS, in the presence of light or heat, peroxides, and carbon tetrachloride, CCl4, the reaction proceeds via allylic bromination, yielding 1-bromopropylene as the product. In this reaction, lighter heat provides the energy to break the OO bond in the peroxide, producing radicals that initiate the free radical chain mechanism. These radicals help generate bromine radicals from NBS, which then performs the hydrogen atom abstraction step at the allylic position. Carbon tetrachloride, CCl4, serves as the solvent for the reaction. We'll conclude the video by exploring the stereochemical implications of radical reactions. Earlier in the video, we learned that radicals are planar, meaning they are sp2 hybridized with the unpaired electron occupying a p orbital that is perpendicular to the plane of the bonding atoms. As a result, when radicals react, they can be approached from either side of the plane, leading to non-stereoselective reactions and the potential formation of racemic mixtures when a chiral center is involved. For example, consider the following reaction. S,3-methylhexane reacts with bromine under photochemical or heat conditions to give a racemic mixture of enantiomers, R and S3-bromo-3-methylhexane. Radical reactions with chiral starting materials do not always result in a racemic mixture of enantiomers. For example, 1s3s, 1-chloro-1,3-dimethylcyclopentane reacts with bromine under photochemical or heat conditions to give two major products, 1r3s, 1-bromo-3-chloro-1,3-dimethylcyclopentane, and 1s3s, 1-bromo-3-chloro-1,3-dimethylcyclopentane. These molecules differ in configuration at only one of their two stereocenters, making them diastereomers. As always, let's do some practice. Predict the structure, including the stereochemistry of the principal monohalogenation product or products for the following reactions. For each product, specify whether it is chiral, racemic, or achiral. For each non-racemic chiral compound, use the Can-Ingold-Prelog RS rules to assign the absolute configuration or configurations of all asymmetric atoms. For each achiral compound, clearly mark the symmetry element whose presence requires a chirality. You may use whichever projection you find most convenient for this purpose. It must, however, be a stereochemically unambiguous depiction. Feel free to pause the video and try this problem on your own first. In the first reaction, the starting material is treated with NBS and peroxides under photochemical conditions in CCl4. These conditions selectively promote allylic bromination, resulting in the formation of two achiral allylic bromination products. Both products have a plane of symmetry in the plane of the paper, making them optically inactive. In the second reaction, the optically pure starting material is treated with bromine and heat. These conditions initiate a radical chain mechanism, which results in monobromination at the tertiary CH position. The reaction yields two monobromination products due to the formation of a planar radical intermediate that can lead to different outcomes based on the symmetry of the molecule. The first product generated is achiral through a point of symmetry, while the second product is chiral, with both asymmetric carbons having the S configuration. As always, thank you for watching, and I'll see you next time.